Hello and welcome back. In this lesson, we're learning algebraic vectors. We just took a look at algebraic vectors in 2D, and now we'll work on 3D vectors. If we understood algebraic vectors in 2D, then it will be easier for us to understand the 3D vectors. Remember that a 3D system is three mutually perpendicular axes, which make 3D or R3. And it is indicated by what we call the right-handed system. So as you can see here, the picture of the hand has the thumb pointing upwards. This will represent the positive z-axis. The pointer is representing the positive x-axis, and the middle finger here, positioned this way, will indicate the positive y-axis. So an algebraic vector can be located anywhere in 3D or R3. Just like in 2D and 3D and R2. So every algebraic vector will have a respective position vector, which is created by sliding the algebraic vector with a tail at the origin. So nothing different than algebraic vectors in 2D. Position vectors can be uniquely identified by the coordinates of the head. Again, same as in 2D. If AB is an algebraic vector, and let's take a look at the coordinates, point A will have x1, or will be identified by x1, y1, z1. So here we have a slight difference because we are in 3D. The coordinates of a point are indicated by three numbers, x1, y1, z1. And point B, x2, y2, z2. Then the respective position vector is OP, with coordinates x, y, z, so three coordinates, because we are in 3D. And now I want you to think of how to find the three coordinates of the position vector using the coordinates of the tail and the head. Very similar to what we did with 2D vectors. So I encourage you to do this on your own, and I will continue writing it here. So for x, we'll have the difference between the x coordinates. For y of the position vector, we'll have the difference between the y coordinates of the head and the tail. And for the z of the position vector, we have the difference between the z coordinates of the algebraic vector, z2 minus z1. Now, a position vector in 3D will have 1, 2, 3 components because we're in 3D. In 2D, only two components, right? X and Y. Here we have also a Z component. So X component will be X2 minus X1. So this is what makes the X component. The Y component, the Z component. The magnitude of the position vector is determined the exact same way as in 2D. But because we have three coordinates, we won't have just x squared plus y squared, but we have z squared inside the square root. So I'm going to say it's the square root of x squared plus y squared plus z squared, which in return will be, since x equals x2 minus x1, and y equals y2 minus y1, and z equals z2 minus z1. So these are two different versions of the same formula. Now, the direction of vectors in 3D is described by what we call direction cosines. So that's what's different from 2D. Remember that in 2D we use theta equals inverse tan y over x. Now in 3D we don't use theta, the tan ratio, but we use what we call cosine ratio. And for this we look at x over the magnitude of AB, which serves as the hypotenuse of the triangle formed with the x component. Okay, so it's a direction cosine, x over AB, direction cosine beta, y over AB, and direction cosine for, or the angle made with the z-axis would be gamma, and it is found by using cosine ratio of gamma equals z over the magnitude of AB. So we're going to take a look at the visual representation of each and every one of them. Now, just like in 2D, in 3D, we use unit vectors to describe any algebraic or position vector. So we're going to have not just two, like in 2D, but we have a third unit vector. So for x-axis, unit vector still I all the time, y-axis is j, and for z-axis, the unit vector is called k. So a vector in 3D can be described in component form, which means just the coordinates. So component or coordinate form means the same thing. Or in standard form, which is expressing a vector as a sum of the, in terms of the unit vectors, okay? So now how do we draw vectors in 3D? And this is going to be interesting. So the coordinates of a point in 3D are represented by a triple x, y, and z. So a point on the x-axis, remember that here is the x-axis. So any point on the x-axis will have some x-coordinate, which in this case we've indicated it by some letter A, and the y and the z will be 0. Similar to this, any point that is located on the y-axis, say for example, right here, will have the x-coordinate 0, the y-coordinate some number, and the z-coordinate 0. And any point on the z-axis will have the x0, the y0, and the z-coordinate equal to some number c. Now the origin is always going to be 0, 0, 0 because it's where all the axes intersect. So we're going to say that a point on the x-axis has y and z equal to 0. A point on the y has x and z 0, and the z has x0 and y0. Now what I'd like us to do is take a look at this particular 3D shape, which is a rectangular base prism. So one of the vertices is right here at 0, 0. And as you can see in here, the point P will define a position vector. I'm going to draw this. Okay, so remember that this will be the XY plane, and we're going to talk about planes in the next unit. This is the ZY plane. Remember, planes stretch on all directions, so in positives and negatives, and this will be the ZX plane. Now this point here is in 3D, and it will have 3 coordinates A, B, and C different from one another. So if you drop this perpendicular on the XY plane, it means that the X coordinate A and the Y coordinate B will be numbers different than 0. But because we are on the XY plane, the Z coordinate is 0. And that's why we see here that the point B has the coordinates A for X, B for Y, and 0 for Z. Now let's take a look at another point. Say for example, we're right here on the x-axis. So on the x-axis, we'll have the x coordinate equal to some number A, but the y coordinate is going to be 0, so is the z coordinate. Here is the point on the y-axis. So for this, I will know right away that since it is on the y-axis, it will have 0, 0, and then this will be the value b. So these are the x, the y, and the z. Now let's take a look at this point here, point D, that is on the z-axis, which means that x is A, y is B, z is 0. Now, as you can see, the points that are on the axis will have only one coordinate different than 0, and the other two equal to 0, depending on which axis we're located here. Now, we're going to take a look at the points on the plane. We actually just did the point B here, A, B, and 0. So now we're going to go at point E, which is on the ZY plane. So on the ZY plane, X will be 0. The other two coordinates will be different than 0. So let's take a look at the next point, this point here, C, for example. The point C is on the ZX plane, which means the Z and the X will be different than 0, so A and C, but the Y value is 0. And if you are on, let's check and see if we had gotten all the points. So 1, 2, 3, 4, 5, 6, 7, 8, we got everything. So this is how we determine the coordinates on 3D. Now, each pair of axes will determine a plane, and planes are perpendicular to each other. So XZ plane is determined by the Z and X axis. That's where Y is 0. YZ plane, Y and Z axis. That's where X equals 0. And XY plane is by X and Y axis, so that's 0. And you can see that the YZ plane is the blue one. It extends on all directions. And the red one is the XZ plane. Now, the XY plane will be the one that is going this way. I think that we didn't go over it, so it makes the diagram a little bit more complex. So let's take a look now at this diagram, at an exercise, example number 4. So what we are given here is, some 3D shape, very similar to the exercise we did before. So we have the point P equal to 6, 2, 4. Coordinates 6, 2, and 4. So I'm going to start off by identifying the coordinates of points A, B, C, D, E, and F as indicated. So let's start with A. And I'm thinking A is located where? On the x-axis. So that means the x coordinate will be 6. The other two coordinates will be 0 because I am on the x-axis. X is the only coordinate different than 0. Let's take a look at the other intercept. So point F is on the y-axis. So since point F is on the y-axis, and I'm going to write this down here. And this was on the x-axis. It means that x will be 0, y will be 0, z will be 0, but y will be different than 0, which means that y will be 2. So 0, 2, 0. The last point on the axis will be the point D. So this is on the z-axis. So since point D is on the z-axis, then we'll say that only z is different than 0. So the other two must be 0. So now we're going to look at the points on planes. So I'm going to start off with point B. So point B is on the xy plane. We said that on the xy plane, z is 0. So when I write the coordinates of point B, I'll say the last coordinate z is 0. The other two are 6 and 2. Next, we're going to take a look at point E. Remember, point E is on the ZY plane. Which coordinate is 0 on the ZY plane? The x. So we're going to say x is 0, y is 2, z is 4. And the last point is the point C. Now, point C is on the plane defined by z and x, so zx plane. Which coordinate is 0 on the zx plane? The y. So y will be 0, x is 6, and y is 4. Now next we're going to take a look at how to plot points on 3D. So I am going to make these axes a little bit more clear. It's when you convert the files to PDF, which is the only way that GoodNotes can read it, so this app that I'm using can read it, it makes it a little bit foggy. There we go. So this is the 3D plane. We have the y, we have the x, and we have the z axis here. So we want to plot the point 2, 4, 6. So x equals 2 will be right here. So 1 unit is equal to 2 here. So y equals 4 would be right here. And z equals 6, which will be right here. So this is how we would like to draw the point. So in order to plot point A, first we're going to use the first two coordinates, the z and the x and the y first. And it doesn't matter which set you use. You can use any set you wish. I find it easier to work with the z, x, y first. And in order to do this, we are going to, I'm going to use the less, more anonymous kind of color here. So we're going to draw a parallelogram. And the parallelogram is drawn by drawing a parallel to the y-axis and a parallel to the x-axis, because we want to go exactly at the point where the two coordinates x equals 2 and y equals 4. So this would be x equals 2, y equals 4. So right here, right now, we are on the xy plane. So this point will have coordinates 2 and 4. Okay? So basically, yes, I said that we draw a parallelogram, but remember, this is a 3D shape. So it's basically the same thing as if we have, for example, x equals 2, y equals 4. We have to create the rectangle. So it's kind of a distorted rectangle, right? Now, from the point 2 and 4, I'm going to go ahead and define the z coordinate. So for z coordinate, knowing that z is 6 units, I will go up 6 units, okay? So it seems that 6 units will be somewhere in here. And I would say that right here at this point, now remember that, again, when we do this, we want to make a parallelogram or a rectangle, right? With the y-axis, with the whole thing actually here. Okay, so we make sure that we are rising 6 units up. And this will be the point A, 2, 4, and 6. Now you can try the next one if you want independently. I'm going to do this with you. So again, I'm going to start with x equals 4 and y equals 6. So let's define all the points actually on the axis first. So we have x equals 4, y equals 6. Now z equals -8, so that makes it -2, -4, right? -6 and 8. I'm going to make this a +8 actually. I think this is a typo. And then we're going to go 2, 4, 6, and 8 here. So these are the 3 points. Now I'm going to start by defining the point with coordinates x equals 4, y equals 6. And again, we do this by drawing the rectangle, which appears to like a parallelogram in here. So this would be the point with x equal to 4 and y equals 6. And from this point, I'm going to rise 8 units. Now remember that we are here on the z-axis, 8 units higher, and we're rising 8 units above this rectangle, which looks like the parallelogram. So for this, we're going to draw a line that is parallel to this one here, right? So that we can create that prism-like idea. So we're going to go 8 units higher here, as you can see. And basically, this is where the point will be. 4, 6, and 8. And you can look at it this way, actually. right? Because that's how you go on the z-axis, this way, and you rise 8. So you rise 8 from here, and that's the parallelogram that you're looking at. And now we're going to express vectors OA and OB in both component and standard form. So the component form of vector OA will be defined by the coordinates 2, 4, and 6. Same idea with vector OB. So the coordinates will be 4, 6, and 8. So these are the components. So in standard form, which means we want to attach the unit vectors, we'll have 2i plus 4i plus 4j plus 6k. And OB, we have 4i plus 6j plus 8k. Okay, so we're going to take a look at 2 more examples, examples number 6 and 7, and follow up with the next video for this. Thank you for watching, and see you soon.